Hi, welcome back. We're going to talk a little bit today about combinational logic in VHDL. So up to this point, we've learned some basics about VHDL, the entity architecture. We've learned how to use some data flow instructions and explored some new data flow instructions. So it's a good time for us to kind of take a detour and look at some of the really neat combinational logic things we can do with data flow statements, and we'll visit some old friends from digital, some things that you've probably seen in your digital past, and we'll bring them into the VHDL world. So let's get started. We'll start with our first component called the decoder, and this is a component that represents the ability to input a code and then have it activate a specific signal. So if we look at this in a block form, we can draw ourselves a little box here. Boy, that's not a very good looking box. Let's try to do a little better job of that. And so we'll have a little block, and then the block will have inputs. So for a decoder, let's say that we'll focus on a standard 3 to 8 line decoder, something you could find in the standard digital chips arena, and talk about how that works a bit. So how these work is, in a 3-line decoder, we would have, 3 to 8, we would have 3 input signals, and that input signal would represent a code, right? And that code basically for us would be a binary number. And then we have 8 outputs, just the 3 to 8. And those 8 outputs would be numbered. So each one would be numbered just like you do in standard bits, 0, 1, 2, 3, 4, 5, 6, and 7. And then if we put in a code, it will activate a specific line. So this is our input code that we would put in. And this is what we're calling it in our design over here is select. So we would select a particular line to activate. And let's say, for the sake of argument, that we're going to put in a value of, 101. So that would correspond to 5. And so if we're going to activate 5, that means this output would go active, but all the others would remain inactive. So we are basically decoding our code. So select has our code of 5, and then it activates a particular pin on the output for whatever that code input is. And you'll notice that we've achieved this goal of creating a decoder simply by using the selected signal assignment statement. A very powerful statement for doing this kind of work. And so every input on the select line is checked, and when it's something like a 5, it will cause the outputs to activate in such a way that in this particular case, let's use a different color there. Bit 5, okay, so that's bit 5, that's the same as this one, gets activated. And so we do it for each one of the possible 8 codes, and we've covered all our bases in a single data flow statement. Pretty nice. Now, the one thing I do want to point out, and I've pointed this out quite a bit, but I think it's important to keep reiterating, and that is that the others clause at the end is very important. And now that we understand what standard logic is, we can understand why the others clause is so important. So what happens here is others covers all other possible states besides the ones that are listed on the right-hand side here in the when clauses. Now, you might say, well, what other possible values could there be, right? I mean, that doesn't make sense. You've got 0, 1, 2, 3, 4, 5, 6, and then this should be 7. That's all the possible values you can have with 3 bits, right? Well, if you're thinking in terms of standard digital, yes. But if you're thinking in terms of standard logic, no. Remember, we've got a data type called standard logic. And standard logic has 9 different bit values that it can have for each signal. So a perfectly valid standard logic signal might be X0 and let's say L. That's a perfectly valid signal, and that would not be included if you had made this all 1. So if you'd said 111 here and not others, then you would have left that one out, which means the synthesis tool would say, hey, you didn't cover all the bases here, so there's something missing, and it would not create the logic you're looking for. In fact, it would likely create what's called an unwanted latch, and that's something that's going to be the bane of our design. We're going to be watching that throughout the whole term to make sure we don't accidentally generate these latches. Basically, the others clause is required in order to make sure we don't have that kind of a situation. So we're going to stick with the others clause on anything that we use for combinational logic. So if we're not intending to store information, if we're not intending for a register or a flip-flop to be there to hold stuff, which is sequential logic, then we're obviously going with combinational logic, which is purely gate-based logic, things with and, or, and invert gates, right? And so the others clause is very key to making sure that we generate combinational logic. And so in all of the examples, you'll see the others clause at the very end to ensure that that's the case. So let's take a look at our next example, and let's talk about the idea of an encoder. Now, an encoder is different than a decoder because in a decoder, we're taking a code and we're activating a particular line. The opposite is true with an encoder. In an encoder, you're basically looking at a particular bit, and then that generates the code. So it's the reverse. So let's draw a quick block diagram here of an encoder. And the idea is you might have 8 inputs here, especially if we're targeting, let's target an 8 to 3 line priority encoder here for our little example. And then if that's the case, then we're going to have 8 input lines. And then we're going to have 3 output lines. Now the output lines are going to represent a code, and that code, and it just so happens to have the signal name code. And then the inputs are independently numbered, just like before, from 0 to 7. Now the way the encoder works is whenever a wire is activated, it will cause the signal on the output to have the proper code for that. So let's pretend that we activate, line 6. Now obviously if we activate line 6, then we expect for the code output to be 110, which corresponds to the value of 6, right? So we're taking an individual wire and we're causing a code to come out. Now here's the problem. What if I activate 2 of the wires? There's nothing electrically preventing us from doing that, and so we have to figure out what to do in that case. And that's why encoders are often called priority encoders, because they give priority to certain signals. In this particular example, we're giving priority to the higher numbered signals. So 6 would have priority in this case over 4. So even though 4 is activated, the code on the output would still be 6. So how do we specify this priority inside VHDL? Well, we can specify it by using conditional signal assignment operator. Okay, so for conditional signal assignment operator, we actually come in and we assign a value to the signal based upon this condition, whatever this condition is. And remember, it does have a priority level. The first one is checked first. The first condition is checked. If it's true, then the output becomes that and it's done, and it finishes. It doesn't even look at the other conditions. If it's false, then it runs down to the next and checks to see if that one is true. And if it's not, then it goes to the next one to see if that one is true. There comes the priority. 7 is checked first, so 7 has the highest priority. And so this situation over here, where we have 2 signals active, still works in this priority encoder because we're using conditional signal assignment. Okay, so that's how all that works. So let's take a look at what's happening here. We have an 8-bit input, okay, and bit 7, if it's active, will cause the output to be a code of 111. But in our particular case, we activated bit 6 right here. So if bit 6 is active, then the output code is going to be 110, which is exactly what we expect. So this is how you use conditional signal assignment for generating some combinational logic. Don't forget, we also have the others clause here at the bottom. We can't forget that others clause if we're trying to generate combinational logic. Let's talk about the next incredibly common, and this is really probably one of the most common combinational logic implementations in most digital designs. Having multiplexers in your system to route signals based on condition is very common practice. So this is one of those functions that you'll see a lot of. So a multiplexer, if you can remember from earlier digital days, basically takes a large number of inputs. In this particular case, we'll consider 8 inputs, all right? And so we'll take 8 inputs and then funnels those down into a single output based upon 3 select lines, okay? So the select lines choose between any one of the 8 inputs. So, as an example, let's say we put 3 on the select lines, 0, 1, 1 on the select lines. If that's the case, then we're telling it to take the 3 signal input and route it to the output, basically making this a digital switch, if you will, and it's selecting which one of these inputs to route to the output. So we're routing an input to the output. Think of a train yard routing a train on a single track. You've got 8 tracks coming in, and you select which track you activate so that that train will go off onto the output. The good old-fashioned train analogy. So the same thing happens, or basically, to implement that function, we use a selected signal assignment statement. And basically, the selected signal assignment statement is made for multiplexers, right? There's your select line. That's what selects the route that you want. If we selected 3, then when it's 3, the third bit of the input data is routed to the output. And that's what this statement is doing. So it's basically assigning this to the output when the input on the select line is 0 and 1. Pretty cool. All right, let's take a look at another function called demultiplexing, which is just the opposite of multiplexing, right? So in a demultiplexer, what we're basically doing is routing the trains in the other direction. We have a single track coming in, or a single line, and then it funnels out. Oops, sorry about that. Let's see, there we go. Oops, wrong one. Where did I go? Oh, there we go. So anyway, we routed out. So basically, we're going to be taking, oops, wrong pen. We're basically going to be taking the other path. We're going to be coming in with a single line, and then we're going to select one of the 8 outputs with which to send our signal, right? So 0, 1, 2, 3, 4, 5, 6, and 7, and then this is our input. And so basically, this represents, well, so we have to have our select lines here. All right. This represents the data in signal. These are the select lines. And this outer one here, all of these taken together, represent the output X, right? So in this case, X is a vector, and it holds 8 individual bits. So the select line, if it comes in and selects, let's just say 5, for the sake of argument, let's say we put 5 there, 1, 0, 1. And then it's going to select this one, and it's going to take the data input and route it to the 5 output, leaving the other outputs inactive in our demultiplexer. So the way this would work in here is we could use yet another selected signal assignment statement, but here's a catch. We're getting to utilize our concatenation operator we talked about in the previous video. The idea of taking vectors and piecing them together. And that's very valuable here because we can put in the data in line anywhere in the output vector we want. Now in this particular case, if the input is 5, which is this one, it corresponds to that line. Now if we go with that line, we see that we start off with 0, 0, and then our data in, followed by 0, 0, 0, 0, 0. That gives us 8 bits, and bit number, let's see, these are numbered 0, 1, 2, 3, 4, 5, 6, and 7. So bit number 5 here basically gets the data in signal. And we did that by concatenating 0 with data in followed by 5 more zeros. You see how we did that? And so we do that for all of the other ones. And so this is a creative use of the concatenation operator to create a unique signal on the output. So this is a really good example of pulling a lot of different things together for us from our previous videos. So let's take a look at another one. So we've done multiplexers, demultiplexers, encoders, and decoders. Let's take a look at the idea of a magnitude comparator. Now, magnitude comparators are pretty valuable if you're trying to look for values to see if one value is greater than the other value or equal to, and those can come in handy when you're looking for thresholds on digital values. And we can do that with with a magnitude comparator. All of the examples I'm showing you here, you'll notice that I've placed examples of actual chip numbers for the digital circuits that these represent, right, in a single chip form. But we can write these in VHDL fairly straightforward. In the case of a magnitude comparator, it's pretty simple. This is a conditional signal assignment statement, and basically we're checking the inputs A and B, and if they're equal to one another, it will activate the low bit of the status output. If they're if A is less than B, it will activate the middle bit, and then if it's others, which would be the A is greater than B, would activate the far left bit. So basically what we have here is a vector. This is a vector that represents 3 values, right? So this value basically represents when A equals B, it goes active. This value represents A less than B, and then this value represents A greater than B, okay? And we've just compressed them into a nice vector because it makes it a lot easier for us to deal with. And so that's how a magnitude comparator would work using conditional signal assignment. So yet another example of conditional signal assignment. The last example that I want to show you is code conversion. And code conversion is also an incredibly common thing to do. One of the most common code converters that you'll see in discrete circuits would be the binary to BCD encoder, because BCD is used to represent numbers in binary for a decimal system. It's called binary coded decimal. And that's very useful for driving 7-segment displays on equipment and other things if you're trying to drive a numeric value. And we can achieve that complex functionality in VHDL with this simple statement. So the BCD output here will be determined by the binary input there. So if our binary input, for instance, is, let's say 1011, that corresponds to the decimal value of 11. And so in a BCD number, the bits are divided into 4-bit segments, with this being the low digit, and this being the high digit. And then if you look at our value for this, that's a 1 and a 1. So in a BCD code, you can only have values from 0 to 9, because there is, for decimal values, that's your number range. And so to represent that in a binary form, we can convert it into this BCD coding. And we simply use a selected signal assignment statement to make that encoding, okay? All right, so that's pretty much it for our discussion of common combinational logic. Hopefully it's helped you see some powerful tools that you can use in the data flow arena for creating combinational logic. Next time, like I mentioned before, we're going to talk a little bit about a more complex example where we pull all this in together to do a practical design using only combinational logic. All right, thank you. See you guys next time.